So today our mathematician spotlight is Rachel Epstein. This is by request, so if you ever want to have a mathematician spotlight, please let me know. Rachel Epstein was previously a visiting assistant professor at Swarthmore, like me. But now she's an assistant professor at Georgia College. Before that, she did her bachelor's degree at Reed College, a small liberal arts college like Swarthmore, and then her PhD at University of Chicago, and then her postdoc at Harvard, and then she came here for a couple of years, and then she went on to be assistant professor at Georgia College. So Rachel Epstein studies computably enumerable sets. So computably enumerable means that you could set your computer to give them to you. So for example, suppose that your favorite set was just the natural numbers, 1, 2, 3, 4, etc. You could write a computer program that outputted that set. Right? It would take infinitely long to output them all, but if you had any favorite of that set, like 247, it would eventually output that number, even if it was a very big number. And similarly, rational numbers, you could set a computer to output all of them eventually. Algebraic numbers, which are the ones that are solutions to algebraic equations, you could program a computer to eventually output them all. Even things like pi, there are expansions for pi, and so you could get your computer to spit out something that was closer and closer and closer to pi. But there are, in fact, only countably many things, so only listably many things that you could do for that, and so there are many numbers that are not then computably enumerable. And so, so she studies the things that you can have a computer spit out and the things that you can't. Pretty neat. All right. So today we'll talk a bit about curves, and then we'll talk about vector fields. And what we'll do for the rest of the course is study curves, study functions on curves, and then study how vector fields, which are like wind, pass across curves. So you could imagine, like, if you have wind blowing across a fence, you might wonder, like, how much wind is pushing against the fence or something like that. And that's the kind of thing that we'll be able to compute. Okay. So before we do that, though, let's do a bit more with curves. So consider the curve. R of t is t times cosine t, t times sine of t, t squared. Okay, so this is similar to something that we studied last Friday. Actually, it's just t times something we studied last time. So last time we talked about the curve cos t, sine t, t. If it was just cos t, sine t, t, well, x and y being cos t, sine t, that means x and y are on a circle. So the shadow of the point then was just going around in a circle. But now we're multiplying it by t. So let's just consider t positive for now. So starting at 0 and going up. That means our radius is starting at 0 and getting bigger. So at the beginning, we're going cos t, sine t in a small circle. And then as t gets bigger, we're spiraling out. So this tells you that at least for values of t that are positive, we're spiraling out. And then t squared. So the bigger t is, the bigger your z value is. So z is getting bigger and bigger. So you're spiraling out and you're going up faster and faster. So this x and y are spiraling out. Z is increasing. So we know it looks something like a spiral that's going faster up and up. And then you might notice, it's a bit of a clever trick, but you might notice that x squared plus y squared equals z squared, equals z. So if we compute this, let's do x squared plus y squared. That's t times cosine t squared plus t times sine t squared. So if you multiply out, you get t squared, well, t squared in both, so I'll just factor it out right now, times cosine squared t plus sine squared t. And cosine squared anything plus sine squared the same thing is 1. So this is t squared, which is our z value. So this tells you that x squared plus y squared equals z. Or in other words, z equals x squared plus y squared. which is something that we know. Yeah.
Do you have
Here? Yeah. Okay, my t and my plus, similar. Okay, so cos squared t plus sine squared t is 1. So this is just t squared, which is e. Okay, so this is a paraboloid. So it tells you that the curve sits on a paraboloid. It doesn't give you the entire paraboloid, because it's just a curve, but it lives on a paraboloid. So the curve is on a paraboloid. So if you wanted to draw this curve in space, a reasonable thing to do would be to draw the paraboloid first, and then draw the curve. So here's a paraboloid. Okay, and here's the origin. And then our curve starts at 0 with a tiny radius, and then spirals around. Something like this. So it's always going counterclockwise. Okay, so it's spiraling around. Okay, so this is r of t. And suppose we had a further question, which is we want to write an equation for the tangent line to the curve at t equals pi. Okay, that's what we want. So when t equals pi, that means we've gone halfway around. So I'll say that's here. So we want the tangent line, which is something like this. Okay. So it's not really going down, it's going up. It's a little bit non-suggestive perhaps to make it look like it's going down, because the curve is always going up. So I'll pick a different point. Here's pi maybe. So the curve, the tangent line is pointed up, and here's our tangent line. Okay, so to write a tangent line equation, we need a point on the line, and we need a vector in the direction of the line. So we need a point and a direction vector. Because this is a blast from the past, from the first week or so of the semester, but we know if we have some point P and some direction vector V, if you want to write the line, the equation of the line through P in direction V, the tangent line is just the point P plus T times direction V. So it means you start here at point P, and then you can go any amount you want in the direction of vector V. So if t is 0, you're just hanging out at P. If t is 1, you've gone 1 in the direction of the vector. If t is -1, you're back here. So this gives you the entire tangent line equation. Yeah? You know it's spiraling counterclockwise? Okay, well, for one thing, it depends on which way you look. But if you look at the shadow from above, the equations are just basically like cos t sine t. So cos t sine t makes a counterclockwise circle. It does matter your perspective, because maybe you could try this. So take your finger. Everyone has a finger, and make a counterclockwise circle in front of you like this. See, it's counterclockwise? Counterclockwise. Okay, now keep it going up, 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 up until it's above your head. You can see it's actually now going clockwise. Yeah? Does it work? Yeah? Yeah. So whether it's counterclockwise or clockwise depends on your perspective. Well, let's suppose that we're looking down on the thing. But if you were looking up at the thing from below, it would be going clockwise. And this is why toilets flush the opposite direction in the southern hemisphere, that whole thing. Because they're flushing the same direction, but you're looking at it from the other side. Cool. Okay. Apparently that's a myth. It depends more on the construction of the toilet bowl than this effect. Okay. So we need a point. So let's see. We need actually r of pi. That's what we need, because we need to know where we are at pi. So let's write down r of t, again, is t cos t, t sine t, t squared. So r of pi is whatever you get when you plug in pi. So pi times cos pi pi times sine pi, pi squared. And now we have to just see what these numbers are. So pi is pi, and cosine of pi, it's something. Maybe we should draw a unit circle. Pi is when you go halfway around. So it gets you to this point here. So cosine of pi is the x value of this point. So -1. So pi times -1 is negative pi. Sine of pi is the y value of this point. So 0. So pi times 0, pi times 0 is 0, and pi squared is pi squared. Okay, so we have our point. So the location of this point is negative pi, comma 0, comma pi squared. I guess it tells you that my picture should be quite a lot higher than it is. Okay, fine. And now, so that's our point. And now we need our direction vector. So we need to figure out the velocity vector, which way this thing is going. So the thing to do is to take the derivative of the position. That gives you how the thing is going, which direction the thing is going. So let's compute r prime of t. So we're taking the derivative of this thing term by term. So it's t times cos t, so we have to use the product rule. So the derivative of the first times the second is cos t plus t times the derivative of the second. So t times negative sine of t. So I'll do cos t minus t times sine t. For the second one, the derivative of the first times the second is sine of t plus t times the derivative of the second. So plus t times cosine of t. I believe there is a mistake on the notes that this has a minus sign, but it should be a plus sign. And finally, the derivative of t squared is 2t. Okay. Now we plug in. So r prime of pi. Let's see. Cosine of pi. Okay, I see. Cosine of pi minus pi times sine of pi, comma sine of pi plus pi times cosine of pi, comma 2 pi. That's the answer. That's the direction vector. Now we just have to figure it out in numbers. So let's see. Cosine of pi is -1 minus pi times sine of pi. Sine of pi is 0. So 0. Okay, sine of pi, that's 0, plus pi times cosine of pi. I think that's pi times -1. So negative pi, and then 2 pi. So we have our point. Here's our point. And we have our direction vector. So now we can write the equation for our line. So let's do that. So, equation for the tangent line. So let's call it, I don't know, L maybe? L of t is our point plus t times our tangent vector. So our point is negative pi 0 pi squared, negative pi 0 pi squared, plus t times the direction that we're going. -1, negative pi, 2 pi. And we usually call this like x of t, y of t, z of t. Error. There's an error. This one should be positive? Okay. Back here it should also be positive. And here it should also be positive. Cosine of pi is negative, right? And this should be negative?
That's incorrect. It's probably because of the mistake on here where she wrote this down as negative. But the minus, it's minus on here.
So on the notes I made, yeah, I took the derivative, I believe, of sine of t, and I got negative cosine of t, which was wrong on the notes. But on the board, I did it right. So Monday morning, Diana took the derivative of sine correctly. Sunday evening, Diana did not. So it's okay. Luckily, all of you are here. Okay, so this is a plus, and cosine of pi is negative, so I believe it comes negative pi. In any case, the idea is the same. So here we are. We start with our point plus t times our vector. And so you can write this out any way you like. You could also put it into one vector, so negative pi minus, or this is negative 1 times t, so minus t, negative pi t, pi squared, plus 2 pi t. You could call it like that, or you could write it out horizontally, negative pi minus t, negative pi t, pi squared, plus 2 pi t. They're all the same. It just tells you, as a function of t, what's your x value, what's your y value, and what's your z value. So there you have it. Yeah. Questions or ideas? Yeah.
I'm assuming this is still material that's going to be on the Friday test.
The Friday test will cover just through triple integrals and not through curves and vector fields. Yep. 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 Yeah. Okay. 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 So let's do a nice application of this. So last time we talked about if you have the equation of a circle, so you have some particle that's moving around in a circle, and I imagine this as putting a ball in a sock and swinging it around your head. It looks something like this. So there's your particle, and it's going this way. So this vector from the origin that tells you where your particle is r of t. I'll color code the same way as before, maybe. The vector from the origin that tells you where your thing is r of t. And then your velocity vector is r prime of t. And if you're going in a circle, the direction of motion is always perpendicular to your vector to the origin. So this thing is always perpendicular here. It doesn't have to be the case that the vectors are the same length. If you're going very fast, your velocity vector might be bigger than your vector from the origin. If you're going very slow, your velocity vector might be smaller. But in any case, they're perpendicular. So we saw that if r of t is on a circle, then r of t is perpendicular to r prime of t. So I'll write that as their dot product is 0. You might notice that this is the same on a sphere. I happen to have brought a sphere today. It has hairs on it for later. But if you are moving along on a sphere, have any of you ever moved on a sphere before? Yeah, you're doing it right now, exactly, yeah. So anytime you move on a sphere, as you tend to do, your direction of motion is perpendicular to your radius to the center of the sphere, or the world, the Earth. So anytime you move, your direction vector is perpendicular to your radius to the Earth. It turns out the reverse is also true. So this we know. You can kind of see it geometrically by looking at the two vectors and looking at this picture here. But it's also true that if your direction vector to the origin is perpendicular to your velocity vector, then actually your motion is you're sitting on a circle or a sphere, etc. And I'll say circle, sphere, etc. because the proof does not depend on dimension. You could be in 4 dimensions or 5 dimensions, although we usually live in 2 and 3 dimensions, usually. So let's prove this. So let's, instead of calling this an also, let's call this a theorem or a proposition. If your direction vector and your velocity vector are perpendicular, then you have to be on a circle or a sphere. That's the only thing that can happen. So we'll prove this. So idea of the proof. We'll suppose that r of t is perpendicular to r prime of t. Okay, that's what we're supposing, because we're saying if they're perpendicular, then you're on a circle. So we'll suppose that they're perpendicular. And we'll show that r of t is on a circle. So one thing that's true about circles or spheres, the thing that defines them, is that your distance from the origin never changes. So we'll show that the magnitude of r of t is a constant, like big R, some constant. Furthermore, a way to show that something is a constant is to show that it's not changing. In fact, we'll show that the derivative of r of t is not changing. The derivative is 0. And in fact, what we'll do is we'll show that the derivative of the squared length is 0. Because if your length squared is 0, then you're also 0. So let's do that. OK, so theorem. If r of t dot r prime of t is 0, then the magnitude of r of t, the derivative of r of t is 0. OK, the magnitude. So your distance to the origin isn't changing. OK, so we'll prove this. So we're interested in the length of r of t. So let's write it out. And like I said, it's going to be easier if we use the thing squared. So the magnitude of a vector squared is the vector dot itself. So for example, if you have the vector 1, 2, you want to know its length, you could dot it with itself. You do 1, 2, dot 1, 2, you get 1 squared plus 2 squared. If you took the square root of that, you get the length of the vector. But if you don't take the square root of it, you'll get the length of the vector squared. OK, and now our trick is going to be to take the derivative of both sides. So let's come through with the derivative. If two things are equal, then their derivatives are equal. So the derivative of the left equals the derivative of the right. So I'll write this left out again. The derivative with respect to t of the distance to the origin squared is, OK, now I want to take the derivative of a product. So to do that, you use the product rule. It turns out that you use the product rule for dot products just like you do it for regular functions. So that's the derivative of the first times the second plus the first times the derivative of the second. So that's r prime of t dot r of t plus r of t dot r prime of t. And that's just an application of the product rule. The dot product is symmetric. U dot v equals v dot u. So these are the same. So this is 2 times r of t dot r prime of t. And now we're supposing that r of t dot r prime of t is 0. So by our assumption, this part is 0. So this equals 2 times 0, which is 0. So this tells us that the distance squared to the origin isn't changing, which tells us that the distance to the origin isn't changing, which tells you that you're on a circle or sphere. So this tells us distance to the origin isn't changing. So r of t is on a circle or sphere or and so on in higher dimensions. Pretty neat, huh? So this has obvious applications for your life. If you are measuring the distance from you to the center of the Earth, you should find that it's constant. If you, at any point, find that your velocity vector dot your distance to the origin is not 0, you are not on a sphere anymore. So you better be careful, because you're either in an airplane or you are like sinking in the ocean. Be careful. Yeah. Yeah. So questions or ideas? Okay, so the idea of this was to play with vectors and curves and equations, and then also to see this sort of theorem proof structure. Suppose this is true, show that this is true, and show how it works. Yeah. Okay. So the thing that we'll be doing for the rest of the semester is like theorems with vector fields. So for most of your life, you've thought about functions. Of course, you're always thinking about functions. You've thought about scalar valued functions, f of x equals x squared or something like that. But now we'll think about functions that for each point associate a vector. So for example, you can think of it as wind. Wind associates to each point a vector. And then we'll integrate vector fields over curves. So actually, you might think of it, I like to think of it as like a stream. The vector field is like a stream. There are fish in the stream. And then you put a net in the stream. And you want to know how many fish are you going to catch. So you integrate the amount of fish that are going through over your net. Something like that. So the first thing to think about then is what are vector fields. So a vector field is a function that associates a vector to each point. So I'll do 3 examples. So for instance, suppose your vector field is 1, 0. So instead of writing a small f, I write a big F with a vector because the thing that you get out is a vector valued quantity. It's just a vector, not a number. Okay, so this tells you for any point xy you plug in, the vector you get out is 1, 0. So I'll draw this vector field. If I plug in 0, 0, I get out 1, 0. So I draw that as the tail of a vector at my point 0, 0 and 1, 0 direction. How about if I plug in 0, 1? I still get 1, 0. How about if I plug in 0, 2? I still get 1, 0. Okay, so for all these points, I get 1, 0. How about if I plug in 1, 0? I get 1, 0. Okay, so the idea is here, for no matter which point x, y you plug in, you get 1, 0. So this is just like a wind, a steady wind blowing east at 1 mile per hour, or whatever your units are. And they don't have to be just at the lattice points. I could draw them other places too. Yeah, okay. Okay, how about if our vector field, f of xy, is x comma 0? Okay? So, now I'm going to plug in f of 0 comma 0. So x is 0 and y is 0, so I get the vector 0 comma 0. So my vector at the origin now is 0. How about if I plug in 1 comma 0? Then I get my vector 1, 0. So at 1 comma 0, my vector should be 1 comma 0. That's supposed to be horizontal. So I just get 1, 0 here. How about if I plug in 1, 1? My x is still 1, so I still get the vector 1, 0. How about if I plug in 1, 2? This point. X is still 1. I still get 1, 0. Okay, so whenever x is 1, I get the vector 1, 0. How about when x is 0? So I did 0, 0 already. But how about 0, 1? This point here. 0, 0, yeah. So, and in fact, anywhere that x is 0, I get 0 vectors. So along the whole y-axis, I can put 0 here. How about if x is negative 1? So now I'm going to look on this line. Negative 1, 0. This point here, my vector is negative 1, 0. So I get these. And then if I change my y value, it does not make a difference. So I get, oops, you should go horizontally. So I get vectors like that. And if I tried x to be 2, then I get the vectors 2, 0. And if I tried x to be negative 2, I get the vectors negative 2, 0. And so on. Okay, this is the line between our pictures. So, yeah?
Can you fill in the vector in the upper right-hand corner on the left graph? No, on the left graph, the 1, 0 graph. Like the vector in the upper right-hand corner.
Sure.
Thank you.
No problem. Glad to be of service. Okay, great, good idea. Yeah, so this one is a vector field for like a steady wind in the east direction. This one might be like if you had a shed, a hemispherical shed. Here it is. And you had water. If rain is falling on the top of the shed, then it's just sitting there. If the rain is falling close to the top, but not so far away, it falls off kind of slowly. And if rain falls on the steep part, it falls quite quick. It drains quite quickly. That might be for this. Like along the ridge line of your shed, nothing happens. But as you go further out, rain falls off faster and faster. Yeah.
Would the slope of that shed, it wouldn't be a circle, right? Because of the way that we're increasing.
Yeah, the slope of the shed wouldn't be a circle. It would have to be maybe a parabola or something like that. You're right. Yeah. Right, because it would be vertical here, and then things would be going very, very fast. Good point. Yeah. Okay, and let's think about one last one. So f of xy equals 0, comma x. Okay, so if I plug in x equals 0, I get 0, 0 as my vector. So all along the y-axis, again, we have 0 vectors. Okay, how about if x is 1? So along the line where x is 1, I get the vector 0, comma 1. So that means for every point here, like the point 1, comma 0, I get the vector 0, 1. So f of 1, 0 equals 0, 1. And then at 1, 1, I also get the vector 0, 1. And at 1, 2, I also get the vector 0, 1, and so on. So along this whole line, I get the vector 0, 1. Then if x is negative 1, I get the vector 0, negative 1. So over here, where x is negative 1, all the vectors are length 1 going down. And then similarly, if you have 2, 0, we get big vectors going up over here, and over here, big vectors going down. And then you could always fill in little guys too. So here where x is about 1/3, you have little vectors going up, little vectors going down. Same thing over here. You could have little vectors going to the right, and so on. Yeah. So it's kind of fun. You get to draw how things are moving. I'm not sure what this one would be. This one just is like movement like this. It's kind of like a highway, except on a real highway, the fastest cars are in the middle and the slowest cars are on the outside. So, yeah. Okay, so if you would, on one side of your paper, there's a vector fields x comma y and negative y comma x, which will be our favorite examples. So please sketch them in. Yeah, great. Okay, and then can you explain? So can you say how you got your thing? Great. So stand to the side. Look out this way. Explain. Good.
I guess for this, it's every corresponding point just, I went ahead and did the axes first. So for every point, you just plug in the numbers for the axes and you solve things. You know these because the magnitude is the same. You would end up having vectors that just went diagonally.
Okay, and then this one?
That one, the x and y are flipped, so I again approached it by going to do the axes first, and then I picked these points, the ones where it's 1, 1, and then plugged in the numbers and solved the vectors.
Okay, nice. Great, yeah. Yeah, so for this one, I think people got the axes and maybe the lines y equals x pretty easily, and then maybe made some mistakes on other parts and had to fix it, which is really good. I like it if you make a mistake and then you have to fix it, because it means that you like learn something, you realize something. So one way you could do this is to realize that if the vector is x comma y, well, that's just saying take your vector from the origin and make that your direction vector. So anywhere you are, take your vector from the origin, make that your direction vector. Here's your vector from the origin, make that your direction vector. So it's like saying that you're a magnet and you're getting repelled by the origin. You're just going directly away from the origin. So you could think about this one as like if you're on a mountain and you have drips of water, at the origin, the water doesn't go anywhere, but then as you go further away, the water sort of goes out in a perpendicular, going away from the highest point. And then this one, so I apologize for this looking like a swastika. It's an important vector field, counterclockwise motion. So for that, I apologize. But it comes up a few times in math like things like counterclockwise motion. So for this one, wherever you are, the further away you are from the origin, the faster you go. And you're always going counterclockwise perpendicular to the motion. So this is just circular motion. So it's like you're on a merry-go-round. Yeah?
Shouldn't, like, at the point 1, 1, shouldn't it be going, shouldn't the slope be, like, -1? Because it should be going positive x and negative y.
Oh, let's see.
That's like negative y, negative x.
So f of 1, 1 is negative 1, 1?
Yeah, I misread that.
It's okay. Yeah. So if we had switched them, right, if we had y comma negative x, then the whole picture would be flipped and it would be going the other way. So it would be, yeah, you would be exactly right. Yeah. I think it's helpful to plug in a bunch of points and actually compute the vectors and then draw them. So yeah, it goes around in a circle. So these are vector fields that we'll think about again and again because they are simple. And they illustrate basically all the properties. We'll have vector fields where things are coming out from a point, and then vector fields where things are just moving around. So these will be our friends. Okay. So I wanted to tell you something, a really cool theorem that comes out of this. So it's called the Hairy Ball Theorem. So this is why I have these wonderful hairy balls. I do not own any of these, but then I asked my roommate if she happened to have any hairy balls, and she had like 10 for me to choose from. So I have this is amazing hairy ball. So here's what the Hairy Ball Theorem says. It says if you, suppose you have a continuous tangent vector field on a sphere. So that means that at every point on the sphere, you choose a tangent vector. So you're not allowed to choose a vector that's going out like this. You have to choose a tangent vector. So if you have a continuous tangent vector on the sphere, there's somewhere where it has to be 0. Okay, so this is how I like to think of it. So you have a tangent vector field. So you have a bunch of vectors, and you want to comb them down flat. So you imagine you have a bunch of tangent vectors sticking out like this, chick, 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 and you want to comb them all down. Luckily, I brought this comb. So if we wanted to do that, we could just comb, like say all to the left or to your right, boom, and it would work, right? We could do that. It might not look very good. The hair you have right now looks better, but we could comb them all down consistently. But if you had hair in the entire head, like not only on your beard, but also this part on your neck where you don't have a head, it's on the inside, it wouldn't be possible to consistently do it in such a way that you could get a nice continuous vector field. So if you tried to, for instance, say, you know what I'm going to do? I'm just going to comb everything to the left. Then you'd be going around. That would be okay, except at the north and south poles. You have a problem. You have something sticking out. You're not sure what to do with it. So it's like vector field of 0. You could also say, you know what I'm going to do? I'm going to comb everything like straight down, right? Everything's going to come straight down from the North Pole. That would be a very nice continuous vector field. And that's like if you just took this ball and you had everything going down. But again, at the top and at the bottom, which you can see here better than you can on my neck, you have a problem. The vector field is 0 or not defined. So that's the idea. Anytime you have a continuous tangent vector field on a sphere, there's somewhere where it's 0. So here you can take it. Good. And try it yourself. Try to find a continuous tangent vector field that's nowhere 0 or that never has a problem. And you won't be able to do it because of this theorem. So if you consider the Earth to be a sphere, which it basically is, and the tangent vector field to be the wind direction at any direction, it tells you that at any time, every possible time, like right now, and right now, and right now, there is somewhere on Earth where the wind speed is actually 0. Not like about 0, but actually 0. Which is kind of cool. And also there's an application to economics, which I've written on the sheet, that if you have an excess demand, you want to be able to sell all your products. You want everyone who demands your product to be able to get one, because then you can sell all your stuff. That would be great. And you can use the Hairy Ball Theorem to prove that there is, in fact, a solution, which is kind of cool. By considering your price to be a point on a sphere, and by considering your demand to be a tangent vector field. It's not something you usually think about, like if you have prices and demands, but if you think about it in this way, then the math can come in and help you. Yeah. All right. Thank you.